Hi. The reason why we'd want to fit a Cox proportional Hosmer model is because we want to interpret the coefficients. The coefficients tell us something useful. In particular, in this video we're going to consider a model where we have a nominal explanatory variable. If we have a nominal explanatory variable, we'll be able to make statements like the risk of group A dying is X times the rate of those in group B. That's the kind of statement you can make. Equivalently, we can say, no, I've said it. So that's it. Simple as that. Although I am doing a biostat example here, this model can be applied in other fields. I'm taking an example from Hosmer and Lemeshow, Applied Survival Analysis, the first edition, chapter 4, and the data is HMO HIV DAT. That data is described in chapter 1. So let's go look at it in SPSS. Okay, the fact that I'm using version 18, I don't think it makes a great difference. Right, the key variables. Okay, what is this data? It's a follow-up study of HIV positive individuals, and we have the variable time here, which is the time from the start of follow-up from which they die, or that we kind of lose track of them, or that they're still alive at the end of the study. How do we know whether they died or not? Whether time represents the time of actual death? The censoring variable. So this particular model allows for censoring. And censoring is a categorical variable. It's coded 1 and 0. Yes or no. So it's coded 1 to say that yes, it's the actual time of death. So individual 1 here, 5 months, this time is measured in months, into the follow-up, person passed away. The second case here, we have 6 months into the follow-up. That's from the start of the follow-up. This individual is coded 0 for censor, so that means that the person was still alive 6 months into follow-up, but we don't know, that person is still alive, or it just dropped out of the study. Anyway, that time records the last time we viewed that person was still alive. So we need this column. We need this column to create our survivor object. And that, in regression, that's a bit like our dependent variable. And then what we're going to consider as an explanatory variable, something that kind of is linked to the survival time, we think is this variable drug, which stands for whether the person had prior IV drug use, and it's coded 1 to say yes, the person had prior IV drug use, and 0 if no history of drug use. Okay, so with our model we're going to be able to say something like people with prior drug use have a risk X times more or less than of death or from HIV compared to people who have no prior history of drug use. That's the kind of sentence we want to make, and the whole point about this short video, I hope, is that we're just going to interpret the coefficient. Alright, let's run the model. We go Analyze, and then we go Survival, and then you go Cox Regression, and this is one I've done early, so let's reset everything. What I want in time is I've actually, it coincides, call it time variable. Status, that's the thing, that's a censoring variable. Basically it's the thing that tells it is it a real event or not. So we've coded 1, meaning that it was actual death. Covariate, that's my x's. The word covariate, reading around, you could see that also goes by the name of explanatory variable, predictor. And we put in drug, coded 1 and 0. Okay, and then what we want to do is we want to have a look at options. In options, we can call for the confidence intervals for the e to the coefficient, basically the hazard ratio. Yes, so you want those typically if you're going to report anything. 95% confidence interval of the coefficient of the hazard ratio. I say it again, I didn't say it properly first time. I want the 95% confidence interval of the hazard ratio. Okay, now do I want anything else at this stage? No. So let's just run it. Okay. Right, so what can we see? We can see that we've got a total of 100, hope you can see this, 100 individuals on this in this follow-up. 20 of them are censored, and the actual events that happen 80. No cases missing. Okay. Where do we want to look next? We want to look down here, the variables in the equation. So this looks a bit, similar to our standard regression kind of output. B, you recall that stands for the coefficient. In this case, and then we also have e to the b. If you've done logistic regression, you'll see it's very similar. Okay, in logistic regression, you'd also have e to the b. But let's kind of just cut that out. That's only if you've seen logistic regression before. For interpretation purposes, this e to the b is more useful because it tells us about the hazard. It's the hazard ratio, and the confidence intervals beside it is also for the hazard ratio. Okay, now let's give you some rules, because when you're interpreting the coefficient, first of all, there's two things. One is the sign, the magnitude. I want to be able to say something like, is the risk higher or lower for one group compared to another? And if I know whether it's higher or lower, I want to say by how much. Right? So there's two things that a coefficient can tell us: the direction and also the magnitude. Right, we can actually do it from this b, or the coefficient, or we can do it e to the b. So let's look at this one. This number here, if it is equal to 0, that tells us there is no difference in the risk of the two groups dying of HIV. Generally speaking, if that coefficient is 0, it tells us that there is no difference between the groups from time to event. If this coefficient is bigger than 1, it tells us the group that's coded 1, which is the people who did take drugs, they were coded 1. It tells us the risk of that group is higher compared to the group coded 0, the reference group. Because you remember, with dichotomous nominal variables, we set up a dummy variable coded 1 if takes drugs, 0 otherwise. So that thing that's coded 0 is the reference category. So we're comparing drug use to no drug use, that way around. So yeah, now if this coefficient is less than 0, it's the other way around. It means then that the risk falls for the group that takes drugs compared to the group that doesn't. Okay, so here it is positive, so that tells us that the risk is higher for drug users. I could also see that from e to the b here. This is basically, if you look at your calculator, there's an e function, right? E to the power of this guy gives you this number, 2.18. And the rule is this: if this number here is equal to 1, that means that there is no difference between the two groups in terms of risk of death from HIV. If this number here is bigger than 1, it tells us the risk increases for the group HIV, for the drug group, and if it is less than 1, it tells us that the risk for the drug group is lower than for the non-drug group. Okay. Here it is 2.18. It's bigger than 1, so that tells us that the risk is from death from HIV is higher for the drug use group. Those rules for interpreting the e to the b and coefficient b always holds for when we're looking at these nominal covariates, nominal explanatory variables. I have to be so careful of my wording. This is just an aside here, because the word covariate, I think the official definition is that a covariate is a continuous explanatory variable. But something which is not continuous, like we've got here, drug use, which is a categorical variable, then would not be a covariate. Hence I'm using the word explanatory variable, or you could usually use the word predictor. But I'm sure that reading around you'll hear people just using the word covariate, whether they mean continuous or not. Anyway, just words. Now we know about the direction, let's talk about the magnitude. For this I want to look at this figure here. This then is the hazard ratio. Well, what is a hazard ratio? Well, it tells us the factor by which the hazard rate is lower or higher to the hazard rate of the group coded 0. So here what we say is that the hazard rate is 2.8, about twice the hazard rate of those without history of drug use. So that's same as saying, if you use the word risk, that the risk of death from having drug use is about, from HIV, let's start again. The interpretation is that the risk of those having taken drugs, the risk of those dying from HIV is about twice of those who have no history of drug use. And basically that's it. Okay, that's the interpretation. If there's two more remarks I want to make are these. This interpretation assumes that the model is correct. Now, this model is probably way too simple to be correct, right? So that takes us on to multiple covariates. You know, just like in regression, when you fit a model, you look at the significance. Is the thing significant? The p-value here is 0.001. Yes, the coefficients are significant. Whether you look at this one or this one, it doesn't matter. It's just saying significant. Second thing, you might have been taught in the lectures that there are three ways of choices for estimating this model. This is technical. It's when you've got ties, i.e. more than one death in a particular period. In that case, we can use the exact method to estimate, or we can use approximations, either the Efron or the Breslow. Now, if you use certain other packages, you'll have options, but this one is the first one I've come across. You have no options, and I've looked around. I think I'm right in saying that there's no options. By default, it runs the Breslow. I know it runs the Breslow because I want to look at this coefficient and compare it to the book. Hosmer and Lemeshow, who also use Breslow, it's the same. Okay. If you had the choice, the exact is the best, but you know, for more complicated model that take very long time to run or not run at all, so it's kind of widely regarded that the Efron is a better approximation than the Breslow. In other words, if you had a choice, you use Efron. However, looking at this book says that whatever you run, they're pretty similar. But hey, if you can run Efron and get something more exact, I'd go for that. Okay, thanks for watching.